neutral. This is force, and the force is always perpendicular to the radius. So how much is the torque? Torque tau is equal to.
Torque is
It's equal to F.
Force times R.
Yeah, it's Fr. The F is 2,000 and R is equal to how much? The R is equal to
0.3
this one.
meters.
This is torque. And the angular displacement in this situation, the angular displacement theta is how much? Theta is how much? We look at this. Through rotation of one rod. So the theta is 1 rod. So the work is equal to tau multiply what? The work, normal work, is equal to tau multiply
And
multiply theta. So this is tau 200 multiply this, and the theta is 1 rod, so it is 64. What is the unit? The unit is what? Unit. The unit of work is what? Is joules. This is the first one. And the second one, what is the final angular velocity if the disc has a mass 85 kg? So ask us to find the angular velocity. The angular velocity, and we already know the work, so we should use the relationship. We should use the kinetic energy theorem. The W is equal to half I square minus half 1 high over the 0 square. The first one, the disc is at rest. So the initial is 0. This one, the initial angular speed is 0. So the work is equal to half is equal to k equal to half I omega square. So the omega is equal to root 2k over I, and the k is equal to the work. And the work is 64 joule. So the omega is this. Now the I, this is the disc. So the I is
just 1/2
is half
R squared.
Yeah, half R squared. The F is 84 kg. R is 0.632 meters. The third one, the rotation kinetic energy. It is just this. We use this one. In this situation, resolution is different from this. In this, we first find by this equation we can also find this omega. Because we use this equation. This is the momentum equation. Sorry, it is the motion equation. The alpha is the angular acceleration. And because W0 is 0, so because we start we start the disk from rest. So this term is 0. So the final angular speed is root 2 alpha. So that alpha is the angular acceleration, and the theta is the angular displacement. So, and the alpha is equal to the tau over I, and the tau is 64, and the I is this one. So we have the angular acceleration is this one, and then we can find the omega is equal to root 2 alpha theta. And then the final rotation kinetic energy. It is the rotation kinetic energy is defined as half I omega square. The omega, the I is this one, and the omega we have found is this. So the kinetic energy is 64 joule. So we can say the kinetic energy is the same as the work. The work is also 64 joule. And the kinetic energy is also 64 joule. Now we look at the angular momentum. When the body is doing linear motion, when the body is in linear motion, the mass is m as a result of v. Then the body will has a momentum. The momentum is p. For the linear momentum, it is divided as the m times v. This is the momentum in the linear motion. Now, when the body is in rotation motion, then we can define angular momentum. The angular momentum, it is defined as the I multiply the L. We use the L refer to the angular momentum, and it is the I multiply the omega. So because we should know the omega, the angular speed is also a vector. The omega is a vector. So such as this is the center. The disk is lying in the blackboard and around in the blackboard plate. So then the omega is this in this direction. So the direction of the omega, it is we should use our right hand. The figure rotates along the omega. So then the direction of the omega is outside, is out from the blackboard. So the L, the angular momentum L, it is also a vector. So the L, it is defined as I times omega. So the L has the same direction as the omega L, as the omega. Now, for particular, such as like this, this is a particular. The mass is m, and the velocity is v, and this is a reference point. This is a reference point. The position vector is r. The position vector is r. So we can define. So for this particular, we also can define the angular momentum. the L is defined as R cross MV. The MV it is the linear momentum. So the angular, so for a particle, the angular momentum is defined as the R cross over the linear momentum. Now, in this figure, this is an object. The mass is m, and this is a circular path of a radius r. So this is the circular path. The radius is r, and acting only by a little force. So and there is a force acted on the particle. So the resulting net torque. The force will result a net torque on the object and increase its angular speed from value of 0 to the value omega in the time interval delta t. And so we can write. So this is a force exerted on the object, and the force will accelerate the object. So we can write the total torque and the torque on the little torque acted on the particle. It is equal to the I times angular acceleration. And the alpha, the angular acceleration, it is defined as the change of the angular speed over delta t over the time interval. So and omega is equal to omega minus 0. The final one minus the initial one. So it is the change of the omega over delta t. So then we will write this. It is equal to I omega minus I0 over delta t. So we define because of the L, the angular momentum is equal to I omega. So this one, omega it is the final angular momentum, and omega 0 is the initial angular momentum. Because the I alpha, so the second term, the net torque is equal to I alpha, and it is equal to the I omega minus I omega 0 over time interval delta t. Because the I omega it is the L, the angular momentum is equal to I omega. So then this one we can also write in vector form. This one it is the change of the momentum. So the delta L, the change of the momentum is equal to I omega minus I0. I omega 0. So it is the change of the angular momentum. So then the net torque is equal to delta L over delta t. So this is a vector. So this is similar to this is analogy. So we look at this. This means this equation means when we exert a torque on an object, then the initial the angular momentum will be changed, and the change rate, the rate of L over delta t over time, it is equal to the net torque. So it means when the torque is large, then the L, the angular momentum will change faster, and if the L is if the torque is large, then the change is faster. If the torque is small, and then the L, a change in slow speed. So this equation is the rotational analogy of Newton's second law, and which can be written in the form F is equal to Q over delta T. In linear motion, the force is equal to the change of momentum over time interval. And the state that the electrical action on object is equal to the time rate of change of the objects and the momentum. So we must remember the torque will change. The torque will change the and the momentum and the rate. And the rate it is determined by the torque. Now we are looking at this problem. So suppose a person exerts 1.4 Newton force perpendicular to the dish, and the radius is 0.26 meter, and for the time is 0.15 second. The first one asks us to find the final angular momentum of the dish. The first one asks us to find the final angular momentum of the dish. If the dish starts from rest and the summing for friction is negligible. The second one, what is the final angular velocity of the dish? Find the final angular velocity of the dish given that the mass is 4 kg and the summing is momentum for rotation is that of this. Now look at this. There is a dish, and a person is a force perpendicular to the radius. This is the radius, and the force is perpendicular to the radius, and the force R. This is the force is F. This is R. And the R is equal to 0.26 meter, and the time is delta T is equal to 0.15 second. The first one, what is the final angular momentum of the dish? And the dish is started from rest. So ask us to find the final angular speed and the momentum. So we should use this equation. The change of angular momentum, the delta L, is equal to the final momentum minus the initial momentum, and it is equal to the I omega minus I omega 0, and because this, and it is the torque multiplied the time, because the initial term is this, the tau is equal to the delta L over delta T, because the delta torque is equal to the time rate of the delta L. So we can write the delta L is equal to tau delta T. The L is equal to L minus L0, it is equal to tau delta T. So in this situation, the disk is start from rest. Start from rest means the L0 is how much?
0.
Yeah, because the L0 is 0. It is start from rest. So it is 0. And the tau The f is already known. F is 2.5. So the tau is equal to f r. And the f is 2.5. And r is equal to
0.26.
Also 0.26. And so this is the 12. So the L is equal to tau t, and tau is 2.5 times 0.6, and t is 0.15 seconds. So this is the final angular momentum. And the second one, what is the final angular velocity? I have to find the angular velocity. So we have find the final angular momentum.
2.91.
So from momentum, how can we find the angular velocity? So what is the relationship between the L and the omega? What is the relationship between L and omega? What is the relationship between them? The omega is equal to, if we express the L by omega, then L is equal to I times what? Times
angular speed.
Yeah, angular speed is omega. So the L is equal to I omega. The momentum inertia times the angular speed. Now we have found the angular momentum. Then we can find the angular speed. Always equal to L over I. And L, original, and I is the momentum inertia of this. For this, the I is equal to half m r squared. So then we can find the omega. So the I is there. So we must remember the torque. It is equal to the change rate of the angular momentum. And the angular momentum, it is equal to I times omega. So if we have find the L, then we can find the omega is equal to L over I. Now we look at the conservation of angular momentum. We have studied the conservation of linear momentum. So in the rotation motion, we also have this conservation law. So because the change in angular momentum over time interval, so the delta L over delta T is equal to the later torque. Now, if the later torque is zero, then it means the delta L over delta T is zero. So what's the mean? What's the mean of delta L over delta T equal to zero?
Angular momentum.
So from this, delta L over delta T is zero, means the L does not change with time. So if we plot like this, this is an axis. The horizontal is time. The vertical is the angular momentum. Because when the delta L over delta T is zero, it means the L is a constant. It is always this value and do not change with the time. So because in that time we chose only 2 points. This is time 1, this is time 2, then this is L1, this is L2, L2 minus L1 is 0, then delta L equal to L2 minus L1 equal to 0, so delta L over delta T is 0. So So means L over than equal 0 means the L it is possible change with time. So if the change in angular momentum L is 0, then the angular momentum is constant. The angular momentum is constant. So the L is equal to a constant. So this means. So this equation, or this expression are the law of conservation of angular momentum. It means if the little torque, if the tau is 0, if the little torque is 0, then the L, the angular momentum, it is a constant. The L is slowly changing with the time. So, we look at this example. This is a scalar, because the friction between the shoes and the ice is very, very small. So we can ignore the friction. So when if we ignore the friction, it means the little torque will be 0. So for this scalar, the angular momentum, it will be a constant. So when he put his hand inside, also initially the moment of inertia is I, and the omega, and the angular velocity is omega. Then the angular momentum is I omega. So when the scalar put her hand inside, then the momentum of inertia is changed. It's changed, and then the angular speed is also changed. And then the angular momentum I omega is also the same. So the L equal to this L, because this is the conservation of angular momentum, because we can ignore the potential, and then we can ignore the torque acted on the scalar. So if when they pulling her eyes and legs in, then the momentum of inertia will be decreased, but the angular momentum is the same. The I omega equal to I omega, that's one, and because the I omega is equal to this one. When the scalar pulls her hand in, then the I will be decreased or increased.
Decrease.
Yeah, it will be decreased, because the rate when her put her arms and legs in, then the mass distribution will in a small range. So the I will decrease. The I decrease, it means the omega will increase. So the scalar can increase her omega, her angular speed, by pull her hand or legs in. Now we look at this equation. Horizontal disc with the momentum of inertia I1 rotates with an angular speed omega 1, and about a vertical friction is eigenaxle. And a second horizontal disc having momentum of inertia I2 and goes onto the first one. Initially, no rotating part sharing the same axis as the first disc. And because their surfaces are rough, the two discs eventually reach the same angular speed omega. So the ratio omega over omega 1 is equal to 1. There is a disk. This is disk 1, and this is the vertical axle. This is I1, by the moment of inertia is I1, and the angular speed is the initial angular speed is omega 1, and we do a second disk. This is a second disk. The second disk grouped onto the first one, and the moment of inertia is I2, and the second disk is and it is usually no rotation. So the omega 2 is 0. Now, finally, these two disks will share the same angular speed, and the angular speed is omega. So now we try to find the omega. So in this situation, for this system, this system is composed by the disk 1 and the disk 2, and there is no other torque acted on the system. So the net torque is 0. The net torque it is 0. We should know the torque. It is acted on the whole system. The system is composed by disk 1 and by disk 2. So the net torque acted on the system is 0. So the angular momentum of the system is conserved. Initially, the angular momentum is how much? It is equal to I1 omega 1 plus I2 omega 2. It is how much? The omega 2 is 0, so it is this is I0. So it is equal to I1 omega 1. And the final one, finally, the total, disk 1 and disk 2, they have the same angular speed, and the angular speed is omega. So the I is equal to I omega, and the I is the total angular momentum. The omega is the common angular speed. So the I is equal to I1 plus I2 omega. And because the conservation of angular momentum, so the I is equal to I0. So we can get the omega is equal to I1 over I plus I2 omega 1. So the omega over omega 1 is I1 over I1 plus I2. So the answer is the third one, C. Do you understand that?
Yeah.
You understand that? The other students, do you understand this problem?
Mm-hmm. Because
there is a system. The system is composed by two disks. This is a disk